All right, welcome to the video on the remainder theorem. Okay, and in quotations here I have put synthetic division. So if you are looking up for more resources on the internet on this particular topic, you can look either up the remainder theorem. Also, you can kind of find some other examples on synthetic division. This particular concept of the remainder theorem becomes very helpful when we start graphing functions, and you don't have to sit there and type it in a calculator over and over and over again. The better you get at this, the faster you'll be able to do math, and the faster you'll be able to evaluate functions. In this case, I have 3 different functions here, and I have I have 6 different examples that incorporate these particular functions. Kind of brings up some different situations that you might run into while using the remainder theorem. So let's talk about what the remainder theorem is. It pretty much helps us, especially in this case. Let's say we're doing f of negative 2, and I need to plug negative 2 into this function for x. It really helps to resolve mostly our use of the negative sign, because sometimes that gets lost in the shuffle, and we may lose it here and there. And so this really helps simplify the process of plugging in negative 2 into a function like this, or maybe even when we get into higher degree polynomials when we have to plug negative 2 into something that's a 5th degree. So we are going to be dealing with some higher degree polynomials in the future. But for right now, we're just going to be kind of using the remainder theorem to just calculate plugging in a number that we'll later use to help us graph functions. All right, so let's dive right in here. Let's first look at the f of x function. Now, the f of x function, this process of doing these problems starts the same way every single time. We're going to look at the degree of the polynomial. The degree is the highest exponent, in this case x to the third. So what I'm going to do is I'm just going to write x to the third, and then I'm going to just put x squared, x to the first, x to the 0. I'm going to write these in descending order. Just starts with 3, 2, 1, 0. Okay, now what these are going to be nice placeholders for me so I don't forget something, especially when I use g of x and k of x. All right. My next thing I'm going to do is I'm just going to write the coefficients that are in front of each one of these terms. So in this case, the coefficient in front of x to the third is 3. Now that also has a name of the leading coefficient because he's the one in front of the highest term. Okay, so that is 3. This next one is 2. This one is 1. We know it's x to the first. This is just the x to the first power. We don't usually write 1 here, but the number in front of that is 1. And then x to the 0 is the guy who doesn't have any x's. All right. So we have this process drawn up for us. I should have drawn this over a little bit further. I'm just going to quickly draw it over here very rapidly here. So we got x to the third to give me a little bit more room to work. X squared, x to the first, and x to the 0. And I have, let's see, 3, 2, 1, and 3. I got these numbers because these are the numbers that are in front of each of these terms, also known in mathematics as the coefficient. All right. I am also now going to draw a box. I kind of call this the house. Now what we're going to put inside the house is what we're plugging in. In example 1, we are plugging in negative 2. So I'm going to plug negative 2 into there. All right. My next motion is I'm going to draw a line here. I'm going to leave myself some room because I am going to put some numbers underneath here. But I'm going to draw this line, and I'm going to drop down the first coefficient, or the leading term. He's going to be not affected by this. He's just going to drop straight down with an arrow, and that's 3. Now comes the process of actually using the remainder theorem. So we have this kind of table set up here, or kind of an organized kind of problem. It's almost like when you see it the first time, it's like a trick, okay? So we're going to take 3 times negative 2. 3 times negative 2 is negative 6. And I'm going to put that number right here, the next slot over. So it's going to go right underneath the 2. All right? I am then going to add these. So I'm going to add these down, so that generates negative 4. Okay? So let me go over that process again real quick with you guys. I'll kind of do it in different ink here. So green, I'm going to multiply up here, multiply, and then I'm going to put that number right down in here. So that makes negative 6. So let me put that back in. That's negative 6. And then I'm going to add these together. So I'm going to add together to make negative 4. Okay? I then start the process over again. So now that I have a new number here, and it's a bad eraser. Now that I have my new number here, I'm going to, let me fill these in because I did have a big eraser. 3. And I drop this down, and then so I'm going to take negative 4 times negative 2. Negative 4 times negative 2 is 8. Again, going to add these together is 9. So we understand the process. I'm doing the same thing every time. Every time I have a number here, I'm going to take 9 times negative 2. That makes negative 18. I add down, and that generates negative 15. The remainder theorem, we call it the remainder theorem because it's the last number that we run out of things to add and multiply together. So if we had negative 15 times negative 2, it would be negative 30, but there's no number out here. So once we run out of placeholders, in other words, x to the 0 is the last one, that is our answer. So when I plug in negative 2, I get negative 15. If you want to try it on a calculator, that's great. If you want to try it by hand, that's also good. But I'm telling you, using the remainder theorem can save you a lot of time and frustration. Also, you'll notice that if I just want to do another problem or plug in another number, all I have to do is erase these particular digits here, and it's already set up for me to put in another number. So in this case, negative 1. So I have 3 times negative 1 is negative 3. Drop this down as negative 1. Negative 1 times negative 1 is 1. Add these together is 2. 2 times negative 1 is negative 2. Add these together and I get 1. So when I plug negative 1 into the f of x function, I get 1 as my answer. So it's a pretty nifty trick in terms of quickly doing something that may take a lot of time and you may make a mistake on to some simple multiplication and addition. All right? So let's talk about another situation. I'm actually going to keep that up. Sorry, I didn't mean to erase that. Let's keep that here just to kind of discuss it as we look at the g of x function now. Okay, so the g of x function, I go through the same process. It's a degree 3 polynomial, so I'm going to go x to the third, x squared, x to the first, x to the 0. And I go through the same process of plugging in, or not plugging in, but looking at the coefficient in front of x to the third. In this case, it's negative 2. Now I notice a hiccup in my system is the fact that there is no x to the square function, or x to the square term. But in all actuality, we could just describe that as a coefficient of 0. We have to accommodate, or have to, that's why I like doing the placeholders, is because it allows us not to forget that we need to compensate for x squared. So that's going to be a 0 there. Then the number in front of x to the first is 2, and the guy with no x's is 3. All right? Then we're going to make the house here, and we're going to plug in negative 2. Now I want you to attempt this on your own, so press pause real quick and see if you can get the correct answer. All right, welcome back. On your first step, you drop down negative 2. Negative 2 times negative 2 is positive 4. 0 plus 4 is 4. 4 times negative 2 is negative 8. Add down is negative 6. Negative 6 times negative 2 is 12. And so our end answer is 15. 15. Now if you were to try to plug in negative 2 into this function, you would have to take x to the third. Negative 2 to the third is negative 8 times negative 2 is 16 plus negative 4 plus 3. So it can be a little process for you, but you'll notice the answers do appear here. But I think this method helps to kind of resolve some problems you may have plugging numbers in. And again, I'm just going to erase this number here, this number there, here, and here. And now I'm just set up for the next example 4. So I'm going to plug in 3. Again, at this time, try to solve this problem on your own and see how well you do. All right, welcome back. Negative 2 times 3 is negative 6. 0 plus negative 6 is negative 6. Negative 6 times 3 is negative 18. 2 plus negative 18 is negative 16. 3 times negative 16 is negative 48. And we add these down, we get negative 45. Now in this particular problem, the numbers do get a little large, so you just have to make sure negative 16 times 3, negative 48. I want to negate you guys from using calculators for this because I really want you to work on your multiplication facts and your just adding and subtracting negative numbers. But anyways, our results are negative 45. Okay, so when we plug 3 into this function, we would get negative 45. And you can certainly check that by plugging numbers in and doing that. Okay, so again, the next one is the k of x function. In this case, it is a degree 5 polynomial. So again, I'm going to start out with x to the 5th, x to the 4th, x to the 3rd, x squared, and x to the 1st, and x to the 0. I need to compensate for every single one of those terms. If I started with x to 100, I would have 100 x's written here. 100 x to 100, x to 99, x to 98. But in this case, we're not going to get that crazy. I believe the highest that I do on your practice problems is x to the 6th power. So let's find out the term in front of x to the 5th is negative 1. Okay, so the coefficient in front of x to the 5th is negative 1. There is no x to the fourth term. There is no x to the third term. The coefficient in front of x squared is positive 1. There is no x to the first term, and there is no x to the 0 term. So even though this is a tiny function, it may look bigger now that we have the zeros included. All right, so now we're going to do our house. In this example 5, we're plugging in 2. And so we're going to go through the process of solving it. -1, -2, drop down. 0 plus -2 is -2. This generates -4. -4, -4 times 2 is -8. 1 plus -8 is -7. -7 times 2 is -14. 0 plus -14 is -14. -14 times 2 is -28. Drop this down and we get -28 as our answer. So hopefully that's the same that you got there. And certainly, again, you can check your answer to make sure it is correct by plugging it into the function. And maybe with a two-term one, it does make it a little bit easier, but we're trying to get practice with this remainder theorem here. Okay, so final one, and thank you for your time here. Try this one on your own, k to the -1, and then I'll work it here momentarily. So if we do this problem, -1 times -1 is 1, so you drop down this, you get 1, -1, -1, 1, 2, -2, -2, and until we get 2 as your answer. Now, the reason why we're working remainder theorem is also because when we start to divide polynomials, we're going to see this make another appearance in the form of synthetic division. So we'll see the remainder theorem pop up multiple times throughout this year and your career in mathematics, because it is a way to quickly plug in a number into a function, a polynomial in this case. It wouldn't necessarily work with rational functions, but it does work with polynomials where we have multiple terms of higher degree. So thank you for your time, and see you all later.